My name is TylerSwope, and we're doing problem 13 on page 46, chapter 2. It's position versus time, stuff like that. We just got a basic, here's our equation right over here, and we're just asking basically what's the position of the particle at t equals 3. So we're taking our equation here, and just wherever you see a t, plug in 3, punch out the number. So we got 3, x of 3 equals 2, it's the initial position, plus 3 times 3. Okay, add our acceleration, which is over here, actually negative acceleration. Let's erase that, put a minus. Okay, and then 1.0 times 3, and you gotta square that. Cool. Okay, so x of 3 equals 2 plus 9, and you multiply that out. Okay, minus 9. Alright, so our x of 3, actually, these are going to cancel each other out, and those cancel each other out, so we got 2 meters, 3 seconds. And then, I don't know if I'm not supposed to do that or not, but you got to remember the sig figs all the way through. And that units is meters, since we're just judging how far the position moved, how far the particle moved. And that's our answer right there. Alright. And then, we also got to find out its velocity at t equals 3. So to find the velocity from this equation, we have to derive it. So we take the derivative with respect to t. Yeah, you take the derivative with respect to t. So we got dx over dt, which is also equal to our velocity of t. So when we do that, take the derivative, the constant's going to drop out. Okay, we take the t and just drop that. So we got 3.0 for the initial velocity. To take our derivative, multiply the power times the number in front. So we got negative 2.0. And drop the t squared down to just a regular t. So that's the equation for velocity. And then also got to just plug in the t now wherever you see a t again. Alright, so we take 3.0 minus our 2.0 times that by 3, just the 3 seconds from before. And then our velocity at 3 seconds equals negative 6. Nope, wrong. Negative 3. Alright. Okay. And then we got to find acceleration for this guy too. So now we take the second derivative. Take d squared of x, which is just the second derivative, that's all that means. T squared, that's going to equal, we just basically drop the 2 on that negative 2t over there. That makes it an even negative 2. So pretty much acceleration, no matter where you're at in time, is going to be negative 2. It's just constant. So that's the answer for that. I'm going to box the answer for the velocity at 3 seconds too. Okay, and that's pretty much it. That solves A, B, and C. And then we also drew up some graphs here. This is a table right here for the time and the position, velocity, and for acceleration. And if you look for right here, it gives us our t of 3. We got it all set right here, which is what we got in the first, second, and third part of the answer. This is the graph for all those. There's our velocity, which is an x to t. It's like your basic, just gravity free fall kind of looking problem. It's not, because it's not gravity for acceleration, but it's got that parabolic shape. And then this is our change derivative of this graph, which just comes out to be constant velocity. It's got a constant change. And then here's the acceleration. And that's pretty much it. You see it's at a -2. And the end. Alright, good.
We good?